building electrical systems for aerospace applications. I'm Naga Pemaraju. I'm a senior application engineer, mainly working in the areas of modeling, simulation, and controls. I'm joined by my colleague, Ramanuja Jagannathan. He's also an application engineer. Working in the same area. We are both from the Controls Design Automation Group at MathWorks India Private Limited. All right. During the webinar, there will be some Q&As, so that you please post your Q&A in the Q&A section, and also there is a separate chat section available. Please, if you have a question, please post in the Q&A. And if your question is something confidential, please, you may direct them to the host directly. Also, there will be some poll questions. You can see them on your poll window. We request you to kindly answer those poll questions. Okay. So the agenda for today, we broadly classified into 3 segments. The first one, I'll be talking about mainly on the more electric aircraft using MATLAB and Simulink. We talk about various technological readiness levels for these electrical systems and how do you build it. And followed by my colleague will be talking mainly on the PMSM controls, which covers the sensor calibration, motor parameter estimation, design and deployment, and also on the battery management systems, mainly on the modeling of the battery pack and how do you simulate and analyze a battery pack. Here's a poll question for you before start. Where are you in your aircraft electrification journey? Are you currently working on a project, or are you about to start a project in next 3 to 6 months, or nothing planned as of now? I repeat, please answer the poll question. Question is, where are you in your aircraft electrification journey? Whether you are currently working on a specific project, or you are about to start a project in 3 to 6 months, or nothing planned as of now. Okay, moving on. Let's start with the first topic of today, the more electric aircraft. So the more electric aircraft, electrification, everything. Why is electrification happening, and why is it important now? Electrification first is mainly a process of adopting a machine or a system using electric power, right? So there are a lot of advantages of going electric, because it improves our efficiency, reliability. It's you can easily control your system, and of course there are a lot of other benefits, like the efficiency of the power electronic device that comes, and also the digital controller, which helps you to do the power controls for the power converters. If I can just list it down, as I said earlier, basically it helps you to be more flexible with your equipment. The way you place your equipment, it reduces your mechanical wear and tear. Of course, the noise, which is a big part of the mechanical systems, they're trying to reduce that, improves efficiency, availability, and of course, easy access to your equipment. So these are some of the benefits that the electric technology brings, and let's see how this can be used for a aircraft. So what is electric aircraft? There are I just simply put a double X here, but there are different different names for these electric aircraft, right? One is a more electric aircraft where we're just doing an electrification of a non-propulsional components. Then comes a hybrid electric aircraft where even the propulsion system is partly electrified, not completely, but it's a partly electric and partly engine-based propulsion methodologies. And finally, it's an all-electric system where everything is electrified. So it's all to do with the motors, generators, battery packs, etc. Right. Uh, Let's see one hybrid electric aircraft, a model. What you see on the screen is a screenshot of the model that was developed in MATLAB and Simulink, and it has mainly three components. One, the aircraft itself, mainly how the dynamics of the aircraft have been captured. The second one is on the power subsystem. How do we understand the power and the torque aspects of it? And then the third one, which says conditions, it's mainly to do with what kind of a profile we want to test our aircraft for, and are we actually considering the environmental factors and how are they? So this it's kind of a full vehicle simulation, right? So there are a lot of things which we analyze having such kind of a system. One, we can understand the aerodynamics of it, any mechanical, electrical characteristics, how are they behaving when integrated with the rest of the system. For example, if I want to simply do the sizing of the battery, this model can help us to understand, okay, what kind of battery sizing I would require, what are the power ratings, can I actually, understand the payloads. All these various problems can be understood at the simulation level using this particular approach, and of course analyze various how the system is performing for various airframe designs. Right, here are a couple of examples. The popular one being the NASA X-57 Maxwell, or you could have your own airframe design. Coming to the load torque model, if you see the subsystem, the first one is, as I said, the aircraft dynamics. Here we are mainly considering it as a point mass dynamics, right? And the point mass dynamics, the power coming out of that point mass dynamics, we're just using for the torque calculations here. And coming back to the power subsystem, there are two basic variants. One is a pure electric and the second one is a hybrid electric. So we have an option to choose a pure electric versus hybrid electric. In the pure electric, it's all motors and DC-DC converters. Whereas with hybrid electric, as we discussed earlier, we are also bringing in the component of engine and generator, so that it's the power is actually split between the engine part and also the motor. So it all depends on your control strategy. When do you need to use the power coming from the motor versus when do you want the power from the engine generator here. So again, these are various methodologies used in building your electrical aircraft, be it a pure electric or a hybrid electric. So let's try to understand various levels of readiness for this technology. So if I see here, again, I have a scale of 1 to 9, and again, there is no explicit demarcation between the levels. But if you see the levels here, the first two basically talks about the basic research, right? The technology readiness levels 1 and 2 mainly focusing on the basic research of this particular technology. And somewhere between 2 and 3 is where you're actually doing your feasibility studies. Okay, I have, say for example, I'm working on a particular type of a motor and I want to change the type of motor, say from PMSM to SR. So is it actually giving me enough good results so that I can proceed? So once we prove the feasibility, then we actually move on to the technology development. So we have fine-tuned, we have identified the right technology, and now we are actually developing that particular technology. That's where we move from levels 3 to 5. Then once we have the confidence that okay, this particular technology has been developed, and then now we actually are ready to demonstrate and then take it to the next level of complete system level development and test. And this levels again is coming from a paper from NASA, which was published in 1995. So And if you actually see this different levels, there are three various types, right? One is a low fidelity or low detail models, a medium detail model, or a very high detail model, right? So the moment you are in the technology demonstration, you are at a very high details. You're giving high details, and that's exactly when you have a high detail. We are actually talking about a production level system, right? And now taking a step below, we actually see how we can actually test that particular level in the real time testing, and then even when we are actually doing a basic feasibility test, we will be doing a lot of desktop simulations here. So let's see the first three levels with an example of a electromechanical drive, right? So in this example, if you see, we have considered a electric drive. Again, it's for the technology level, readiness level 1. It's for us. It's mainly an ideal electromechanical drive, right? So it's we are not really considering any of the any of the dynamics, or not even a feedback controls involved. It's a purely ideal system in this particular case. Now, when we want to move to the next level, that's where we want to slowly introduce a little bit dynamics, and then introduce FOC feedback controls. That's what you can see in the two screenshots here. We have introduced the PMSM motors, and also the torque control and speed control. So we are actually increasing the level of complexity. However, we have not increased with respect to the inverter. We have still considered it as an average level inverter, right? So we are not actually considering the switching effects of it. Now, when we go to the next level of readiness, that's where we will also include the switching aspects of it. So that's where we'll actually have, say, if you're having IGBT or a MOSFET-based inverter, you have all the 6 IGBTs, and you're actually trying to understand how my inverter is working, and how this switching is impacting my rest of the system. So it is even more further detailed system. So these are various levels of which we can use, again, based on where you are in your project. If you are in the initial phase or in the feasibility phase, probably you will be sticking with ideal electromechanical system, or maybe an average value converter, like in the previous slide. But if you are ready for a complete implementation, and then you are ready for a technology development, and that's where you will probably get onto the having more details in your system and trying to understand that particular system. So one is the level at which we are. The second one is we also need to understand the power quality aspects of it. As we're discussing about the electrical system, the power quality, analyzing the power quality is one of the key criteria, right? So for example, in this case, I have a system with a generator with various AC bus and DC bus and various loads. On when my load is turning on or off, that will impact my voltage curve, that voltage that's coming out of this particular system. So I need to consider various harmonics as well, right? So if it's a simple plain system, I have a nice sine wave, as you can see. But the moment we try to introduce more more of this switching, and also understand the impact of the loads, a lot of harmonics comes into the picture. We need to analyze those harmonics, like probably we'll be doing like an FFT analysis of the data. So we use Simscape Electrical and MATLAB to understand these aspects of it, and further analyze our power quality. Talking about Simscape Electrical, Simscape Electrical is a tool from MathWorks, is a part of Simscape products, which helps you to do the physical modeling in the electrical domain. We can do a lot of electrical, mechatronics, power systems, and also you can evaluate any analog circuit architectures, various kinds of mechatronic systems like electric drives. Talking about electric drives, PMSM, induction motors, etc. Right. You can also try to see how my system, when it is connected to the grid, how my system is how my system is working, and all of those aspects of it. Couple of things which I want to highlight apart from the one we discussed. One is, if you're working on any other third-party softwares like Spice, you can actually import those Spice netlist into MATLAB Simulink, and then you can actually understand the understand how my system is behaving in the simulation world. You can go from a very ideal switching to, you can increase the complexities, and we do provide a lot of application specific examples as part of this particular toolbox. And of course, last but not the least, we do support C code generation, and a lot of our customers are using this for hardware loop simulations. Let's try to understand the use cases for which Simscape Electrical can be used. So if I just divide the whole ecosystem into three parts, right? One, as an engineer, probably I want to understand the system level behavior. Maybe there will be a sub team which will be mainly focused on the component validation, right? And there will be one more team which can be used in the component level design aspects of it. So this Simscape Electrical can be used at all the three different levels. So let's take with this example. In my system, I have a power, motor, and a pump, right? Now, for my system level behavior, I really do not really care about details of my power, how things are, and also if I just have a plot of my power, you can see the nice curve here. So this simulation, probably you can have up to the hours, with respect to time frame. And you see, I can actually simulate, for multiple hours of simulation can be done without any issues. Now, for a component level validation, if I take a power system, I need to understand various switching dynamics of it, right? So that's where I will slowly introduce the concepts of AC/DC, AC/DC converter or DC/AC converter, the bus, all of that, and then I can actually run into minutes of various minutes of simulation here. And now for the further component design, if I just take an AC/DC converter, for the component validation, probably I might be considering an average value converter. But when I come to the design, component design aspects, I actually will have a detailed, switching components like maybe an IGBT or a MOSFET. And then, here we are actually dealing in terms of microseconds of simulation, right? So we can get the details to this particular level of simulation. So the same as if I have if I am working on semiconductors or motors, let me pick motors for now. Again, we can perform for a system level behavior. We can understand the steady state equivalent circuit. Again, for the component level validation, for the motors, again we'll be looking into the thermal effects of it, and maybe for the component design, we are looking at the flux and angle application. So here are some resources. There's a white paper, technical article on our website. I would encourage you to, read this. It gives a good, understanding about real-time simulation and testing of power electronics for a more electric aircraft. Okay. Then comes, since we're talking about the electric aircraft, this is how a notional more electric aircraft looks like. You can see various levels here where subsystems, the bottommost four, we are talking about the 4 LV motor drives, which can be considered as a load, acting on our system here. Then comes our DC power conversion, where from the load, we are actually, looking into the DC aspects of it. Then we are talking about various generators, motors, and a battery pack here. And then finally, we're talking at the turbines aspect of it, right? So in this case, in this particular example, we are using a Brayton cycle gas turbine. So if we need to start building this, where do we actually start, right? So building a system, such a complex system, is a very tedious task, and a lot of times we'll end up at the wrong side. So what is the right way of doing this? Let's look into that. And before getting there, some of the things to look out for is simulation speed, the accuracy, the reusability of the components, and of course the connectivity between various components. So if such a system, if these are my criteria, right? Where do I start? It's not ideal to put everything together and run the system and then get into the trouble. So the ideal way is maybe you start with having a power source, an ideal one as long as you can, and then start with the loads. First start with the loads and slowly start building on top of that. So if we can explain that, probably in this case, in the system, what we are looking at, let's start with, one aileron, which is acting as one load for me. then slowly build up that, and then in this case I'm just trying to have four load systems, which is connected to which is connected separately but trying to have a constant voltage source. Now I'm getting into the next level of introducing the DC-DC voltages, and then we're not actually considering the systems of various motors and generators. And then now slowly I introduce a battery pack. Right now I can understand, okay, for all these four loads, whether my battery pack is able to sustain. You can do all the trade-off analysis at this level. Once you get more confidence, that's where you introduce the final generators, motors, and also the turbines. To start with, I would recommend you to start with an ideal turbine. Once you have more control of how things are, then probably you can shift it to Brayton cycle gas turbine. Right. If I just quickly show you how that particular model looks like. Here is the same model what we have just seen. Here I have the ailerons, the DC-DC. If I just look into the aileron part, it's a simple inverter and a motor circuit which I've considered for one of the ailerons. And as I discussed, probably start with I'm considering an average value inverter and a PMSM motor. And once I have that, I'm getting into the DC-DC levels and then the battery packs. Again, we have considered the basic version of the batteries, but in today's session, we'll be getting into the details of about the batteries and the motors. Just talking about the Brayton gas turbines, this again, we have used some of the components from our Simscape components. We have used turbines and compressors, etc. So for some of these components, we have used the custom component built using Simscape language. Again, Simscape as a tool helps you to build your own components. We are not getting into the details onto this particular topic, but if you are interested, please reach out to us. We'll be happy to discuss further post this session, or we can reach out to you separately. All right, so moving on. So we can perform the desktop simulations as well as the real-time simulation. So again, the same model, we have tested this running on a SpeedGo real-time target machine, and we have identified how are my tasks being executed. So in this case, we have just had the task execution time profiler, and you can see the various tasks at various rates that you can see. And suppose if my system requires multiple sample times, right? For example, I want to have my LV system at 10 microseconds, whereas my MV system at 50 microseconds, right? So then I can actually have a multi-rated model incorporated into my system, into this particular model, and run various multiple sample times in the same model itself, so that I can get a feel of how things are working. And again, we can actually look into the execution rates of each of this. And for example, the topmost one, you're seeing the average value versus the full switching and how things are working. And you can do the further detailed analysis of this having a multi-threaded system. So I would leave with one more poll question before my colleague takes over from here, who will be focusing on the motor controls and battery management system. The poll question now is, which area of the aircraft electrification are you working on? Please answer this. Are you working on energy or a battery management system? Or are you working on motor controls or power converter design? If you're also working on the code gen aspects of the motor controls, you can select the same motor control aspects of it. Are you working on the power system analysis and design? Please use the third option. Or if you're working on any other electrical system which is not mentioned here, please choose the fourth option. As you answer the poll question, I will hand over now to my colleague Ramanuja.
Yep. Thank you, Naga. Can you let me know if you can see my slide and I'm audible?
Yes, Ramaja, I can see your screen and you're audible.
Okay, great. All right, everybody. So, as Naga mentioned, please, answer the poll question before we proceed to the next section of this webinar. All right. Okay. So, moving on. So, today we have seen until now how to model the electrical system of an aircraft. So, we are talking about a system level model, and Naga mentioned that we also need to do component verification and then integrate it to a system level model, right? So, in that point, so we will be talking about two specific subsystems, what you find in an electrical aircraft. One is on the motor control and another is on the battery management system. We will see how to design these subsystems using MATLAB, and then probably once the design is done, we will be integrating them to a system level model and then do system level studies. So the motor is an integral part of your electric aircraft, right? So if Naga spoke about the different nomenclatures of the aircraft. So if you're doing a full electric aircraft, probably your entire turbines are run by the motors, or in hybrid architectures, you're partially running your turbines with the help of motors. So they become really imperative to model very accurate motor control systems. Now, when we talk about motor control systems, the most famous architecture is the field-oriented control, which you could see in the screen over here. Now, the field-oriented control has two loops. One is the outer speed loop and then the inner current loop. Here, the inner current loop is a bit complex because it performs some complex mathematical operations such as the Clark and Park transform. And also, it's more demanding in a way that you need to execute these operations at a very small sample time, such as 50 microseconds range. So it's really imperative that you're deploying efficient control algorithms to your embedded hardware to make these algorithms run in time. Now, we will be seeing how Simulink can be used to design these algorithms and deploy them. So, our customers across industries have been using Simulink to prototype motor models, control algorithms, and then do extensive closed-loop verifications in simulation environment. Now, once they are satisfied with the simulation results, now they are happily deploying these control algorithms to the embedded hardware to check in real-time situations. Now, with this method, a lot of customers report that they were able to develop their control algorithms much more quicker. In one example, one of the customers used Simulink to develop motor models and then develop control algorithms alongside. Now, the main challenge here is that they were able to develop motor models even before the actual motor hardware was available to them. So they were able to parameterize the motor using the datasheet, and then they were able to test and design control algorithms. Now, once the control algorithms are designed, they're able to deploy to an embedded hardware and test it in real-time environment. And all of this happened even before the actual motor was available. Now, they quoted that the development time reduced into half, and that's the kind of benefit what they got when they were designing their control algorithms using model-based design approach. Now, in 20A, we added a new product called the Motor Control Blockset, which enhances your motor control design workflows. So firstly, Motor Control Blockset provides you off-the-shelf blocks which are used for your car park transforms and which can also be used for your sensor decoders and sensorless observers. Now, these blocks are implemented in such a way that the code which is getting generated from them are more efficient and they could run much faster rates in your embedded hardware. Now, additionally, there are workflows such as parameter estimation and controller auto-tuning, which we'll be seeing shortly. So when we talk about motor control, a typical workflow looks like this. You would start with calibrating your sensors, and then parameterizing and modeling your motor models, designing controllers, and then you go on to deploy it to your real hardware and check in real-time situations. So we will see how Motor Control Blockset lets you navigate through this workflow with its capabilities. So the first step in the workflow was sensor calibration. Now, typically for sensor calibration, you would take your motor to a lab setup and then perform some experiments to get some data, and then you would estimate the sensor calibration. Now, using Motor Control Blockset, we provide some ready-made workflows, which basically codifies your experiments into Simulink models, which you deploy it using code generation into your embedded hardware. Now, the embedded hardware does the testing for you, and Simulink is always connected to the embedded hardware using Simulink serial communication protocols. Now, here we'll be seeing one example of how to calibrate the Hall effect sensors. Now here, what you see in front of you is a model which has a codified implementation of the procedures required to extract data for the Hall offset. Now here, this model contains algorithms which you could find it over here. Now this algorithm typically helps in finding the motor offset. Now what we do is we deploy this algorithm into the embedded hardware using C code. And once the algorithm is deployed, now we are maintaining a communication between the Simulink model and the actual embedded hardware. Now here, you could see that we can turn on the algorithm from Simulink. And once the algorithm is turned on, you would see the algorithm deployed in the embedded hardware gets triggered, and it's trying to perform the experiments to estimate the sensor offsets. Now, you could see the experiment is going on, and once the experiment is done, the model in the embedded hardware would send back the offset data to your Simulink model for your visual results. Now, moving forward, in a similar way, we could also codify the parameter estimation workflows into your embedded hardware and then perform experiments to find out the motor parameters. Now, in this case, you again see a motor model. You again see a Simulink model here, which has some of the motor parameters included, and which shows some of the motor parameters which would be estimated during the experimentation process. Now, moving forward, we have another model. Now, this model, what you see right now, it contains all the codified versions of the experiments needed to be conducted with the motor to find out these parameters. Now, we deploy this particular model into your embedded hardware. And after we deploy it, we use the original model as an interface to get the results. Now here I could turn on the original model, and once the model starts, it triggers the algorithms deployed in your embedded hardware to run the experiments to obtain the motor parameters. Now, as the experiments are being run in the embedded hardware, you could see the parameters being identified and being displayed in the Simulink model, which happens via the serial communication between the embedded hardware and the Simulink model. So using this sort of an automation, we would be able to quickly prototype the algorithms required to find out the parameters, deploy them to the embedded hardware, and using serial communication, also get back the identified parameters into Simulink, which you can reuse in your simulations later. Also, you have other methods for parameterization, such as using your datasheet models, datasheet parameters, or your CFD models, which you could use to parameterize the motors. Now, once the parameterization is done, the next step is typically to modeling the inverters and the motors. Now, here we have some variants. We have an average value inverter where typically you're having a lump parameter motor model, which has some basic motor parameters. And then if you go into the inverter subsystem, you would see an average value inverter. Now, this could be really useful in quickly estimating the control parameters and iterating over several design parameters. Again, we have another variant which talks about the switching variants of the inverters. Now here we have a PMSM motor taken from Simscape, which provides more details for parameterization. And if I go to the inverter subsystem, here I'm seeing that we're actually simulating all the 6 separate gate pulses of the inverter. And then I'm also able to select which semiconductor device I would be using for simulating the switches in the inverters. Now, with these two variants, we'll be able to design and also verify the control algorithms in simulation environment. Also, Simulink provides you options to include saturation effects and harmonics effects in the motor models, basically by providing blocks which are available in Simscape electrical libraries. Now, once you have made the motor parameterization and models, the next step is typically into designing your control architectures. So we saw how FOC algorithm contains several complex mathematical operations. Now let's see how they get used in your models. So in this case, I'm seeing a closed loop of a FOC control already implemented, and we see the speed control and the current control loops. So getting into the speed control, we could see that it has a PI controller to regulate the motor speed. And then let's move on to the actual current control block. So when we go into the current control block, the first thing we see is the sensor data which are getting acquired from the feedback sensors. So here we see that there's a phase currents being acquired into the block, and also we see that the position sensor data is being acquired. Now, after you acquire the position sensor data, the next step would be to decode it to obtain the actual motor positions. And for that, you need to implement an algorithm for the decoder. With motor control blockset, you get these blocks ready-made from the library, which you could directly use in your models to implement such decoders. Moving on, next going into the control systems subsystem. So once I go into control system subsystem, here I could see that it basically has some intensive mathematical operations such as the Clark transform, Park transform, the inverse Park transform, and the space vector generator. Now, all these blocks are available off the shelf from the motor control blockset library, which again you could use for your FOC architecture design. As I mentioned before, these blocks are more efficient for code generation, and hence when you deploy these algorithms, you would get more optimized code which comes for these algorithms. So once the architecture has been set up, the next step is typically into tuning the PID gains so that your control system is more stable. So motor control blockset provides you empirical functions which takes in the motor parameters and the inverter parameters and then gives out PID gains which make sure the closed loop system is in a stable operating region. Of course, you could use Simulink control design to utilize the extra capabilities of designing the control gains by yourself using the frequency techniques or root locus techniques. So once the control algorithm is being designed, now we go into the closed loop simulation environment where you test the closed loop system into several operating conditions. Now here, I want to show you that we are testing the algorithm using both the average model and the switching model based inverters. Now, when we overlay the results among each other, we could see that the average value inverter overlays perfectly with the the model with the switching taking into account. So we see similar results, and hence we are sure that the average model inverters are working fine. Now you could use this kind of simulation results to fine-tune your control gains, or go back and then reiterate your design process and change some of the design parameters. Now, once you're satisfied with the design in a simulation environment, the next step is typically to deploy the algorithm into a C code, which can be done using some of the coder products what we provide. So Simulink models can be deployed to an ANSI C code, which can target any processor. And also we support both floating point and fixed point implementation. So once the algorithm is designed, now we can actually deploy that to an embedded hardware and then check in real time how the control algorithm works with the actual motor. Now again here, I still have a connectivity with my embedded hardware and Simulink model using serial communication, and then I'm able to give set points changes to the embedded hardware via my Simulink environment. Now this forms a testing environment where you could use Simulink to automate your real hardware test cases. So we saw how to implement the field-oriented control using the motor control blocksets. Now, next, my focus would be on another subsystem, basically the battery management system. You will see how to model your battery packs and how you can do simulations and analysis results using the models what you made. Again, coming back to our system model, battery is an essential part of your electrical network in aircraft. In case of full electric, it's acting as a single source of power. In case of hybrid electric, it's acting as a it's acting as a component which could store and then retrieve power based on demand. Now, the starting stage to model these battery packs will start with modeling a simple battery cell, and then you could scale it up to model an entire battery pack. When you talk about modeling a single battery cell, we usually use the equivalent circuit model of the battery to model that in Simulink environment. So the equivalent circuit typically contains an open circuit voltage source, which you can see as EM over here. And then it also contains the R and C components, which are used to model the electrical dynamics of the battery. Next, these components need to be parameterized, and they typically depend upon the state of charge and the temperature of the environment. So first, let's see how to model this kind of an equivalent circuit in Simulink. As Naga explained before, we have this product called Simscape, which is used to model multi-domain components, and we go to Simscape to model the electrical components. Specifically, go to the electrical sub-library under the foundation library to find out voltage sources and then resistance and capacitance blocks, which could be modeled, parameterized using a lookup table. Now, once the modeling is done, the next task is to parameterize these different components. So what we do is that we conduct some standard tests on the real battery and then obtain the experimental results to go and fine-tune your model parameters. So in this case, on the right, you could see that there is a pulse test being conducted, which gives a relationship between the current drawn and then the voltage profiles of the battery. So we take such a data, we bring it into simulation environment, and then try to fine-tune the battery parameters. Let's see how we do that. So we have two models over here. One is the model of the actual battery, and the other one is the actual field battery sitting in a laboratory. Now, what do? We excite both of these entities with the same input. So a similar input is given to the model, and the same input is given to the actual battery pack, what you have in your laboratory. We check the output of these both entities for the given input. We see if these both outputs are equal to each other. If they are not, then it means that the model is not replicating the actual battery performance from field. So we go back to the model and then change the parameters which are used to model the battery. And we do this until the performance becomes equal. And once they are equal, we become happy, and then we say this model what we have could be used to simulate the actual battery what I have in my laboratory. Now, typically, we use current as an input, as in the pulse test what we saw, and then we see the voltage profiles and then try to match these voltage profiles between the model and the experimental setup. So once the modeling and parameterization is done, the next step is typically to go on to simulate these and then do some analysis on that. So here we see that first, initially we are using this arbitrary values, and then we see there is no match, and then we see that there's a perfect match when we do the optimization settings. Now, as I said before, the next step is typically to go and do the simulations. Now here we are actually implementing the cell dynamics to see the electrical dynamics here, and also we could simulate the thermal effects of the cell by connecting the thermal blocks from the Simscape multi-domain library. So once we model the battery cell, the next step is typically to scale it up to a battery module where we connect several cells in series and then try to make a battery module. Now here you could notice that we are simulating thermal effects as well as the electrical effects of the battery. Next, we connect the battery modules in a series parallel combinations to get the battery packs what we actually have in the setup. Now, once we have made the battery pack models, the next step would be to go on and then develop some control algorithms to design the safety aspects of the battery. Now, here we have the plan model, which is basically the battery module, what we saw. And then we can use Simulink and Stateflow tools to develop battery algorithms, which could be used to control the battery working. Now, once we make such a model with the battery controller and the battery model, we can connect them in closed loop and then test it with them several drive cycles and then see how the battery performs. So in this particular experiment, we are trying to see how the battery responds in a particular drive cycle. Now here we see that initially the current is negative, meaning that there is a discharge occurring. But then later we see that the current becomes positive, hence there is a charging phase of the simulation. We could also see the corresponding state of charge estimates, and then we could see the voltage value being increasing when there is a charging occurring. One important thing to notice is the effect of temperature while we do the charging and discharging. it's very important we keep temperature within the limits, and these kind of simulations help us in understanding how temperature varies over the usage of the battery. Of course, we could also test the battery for unsafe conditions and then see how the controller performs. Now, what we do for that is we can go for hardware in the loop testing, where we actually deploy the controllers from the closed loop environment to an embedded hardware. The models what we had for the battery, we can deploy them to an real-time simulator. And once that's done, we use some I/O cards to interface the real-time simulator with the embedded hardware. Now, in this kind of a setup, we could actually simulate some very faulty conditions, which could be very dangerous to simulate in an experiment in the lab, and then we could see how the controller responds. Now, this kind of a setup helps us in covering all aspects of the batteries, and then we will be able to test and validate the complete working of the controllers. So with that, I end my talk on the battery management system. So in a review, we saw how today the electrical aircraft will be simulated. We saw how the system level simulations can be built. We then focused on two specific subsystems. One is on the motor control and another is on the battery management system. So now I would like to understand, having heard from us the capabilities what we have, I would like to understand how you would like to reach to us, and what sort of engagements would you like to have further. Now, some of the options here is that you could reach to us to have a technical discussion where we would talk about in detail about the product features, and also we could talk about other aspects such as power converters or other electromechanical modeling. Probably you might be interested more in the training aspect. You could check that. If you're looking to try out the products or to purchase a product, you could choose the option 3. Also, you could let us know that if you're not ready with the above options. So the time is closing, so please fill up the poll before we go on to the question and answer session for the day. Yep. So also, we would like to understand how you would rate us in today's presentation, whether you found it useful or how the overall content was. So again, you would see another poll in which you could let us know how the overall content was today, how was it, and you could rate it between 0 to 10. So I'll leave you some time here. So me and my colleague Naga will be looking into the question answers, and then probably we'll get back to you some answers. So please feel free to post your questions in the question sessions, and give us a minute time to go review them, and then we'll come back to you. So meanwhile, please fill up this questionnaire in front of you. Finding is around building aircraft simulator models for training pilots and aircraft crew, and the question is if we have any Simulink model to do that. So to answer that, we have worked with several other customers to build certain models. I need to check if you have an implicit model which is shareable to the public, but then we could have further discussions and then see if we can build similar models for your project. Another question asks about how do we cater for the changes in battery parameters over time. So how to make sure the battery model is working accurately for the changes over time. So one thing these battery models have, what I showed today is also the state of health. So basically, you could parameterize these batteries, how the health would degrade over the usage. You have in the particular blocks what we show today, you could use that to actually model the battery health degradations. Okay, another question: any EV HEV use cases? The electrical traction components most different.
There are a lot of questions on sharing of the PPT and session. So post our session, we will be actually sharing you a link to the recorded webinar, which also has the slides in the PDF format, so you can actually access all the PDF, all the slides what we discussed today, and also you can review the complete recording of this webinar.
Sure.
Way to find training material on motor controls modeling, from simple average modeling to I think complete switching model. So as we discussed, there are different ways. It depends on what level you're trying to do. For example, we do have blocks for average model converters, and if you're talking about the complete switching model, probably we will be using the component levels like IGBTs and MOSFETs, which are also part of the Simscape electrical library. And we do have examples on this. So I would, if you can reach out to us separately, we can have, we can have a discussion and we can share something for you. Please share your contact details, and we'll be happy to get back to you on this topic. And there's one question on the UAVs. Do you have any? Can you show how to model the control system of a UAV? We do have some webinars already on our website. But yeah, definitely we can share you the link to the existing webinar on a UAV. We just recently did, I think, a month or 2 months back on the UAVs part. So we'll be happy to share that aspect.
Yep. So for the want of time, we can move forward and then probably take the rest of the questions over email. We would probably respond to you. So I want to close this webinar, by giving you some information to the training services what we offer. So we do offer trainings on the different tools what we saw today. For example, we do offer a training on Simscape to specifically build electrical power systems and do the analysis what we discussed in today's webinar. So with that information, I want to thank you all for attending the webinar. We hope you found it very useful. So for the questions which we are not able to answer today, probably we are going to get back to you soon via email, and probably we can have later discussions on how to make your aircraft electrification journey using MathWorks tools. So again, thank you all for attending, and hope to see you during post interactions sessions. Thank you.
Thank you very much.